Good day, students. Welcome to mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problem number 5 of the 2017 AP Calculus free response question. This particular problem focuses on particle motion. We're looking at position, velocity, and acceleration. All right, question 5 reads, two particles move along the x-axis. For 0 less than or equal to t less than or equal to 8, the position of the particle p at time t is given by x sub p of t equals the natural logarithm of quantity t squared minus 2t plus 10, while the velocity of the particle q at time t is given by v sub q of t equals t squared minus 8t plus 15. Particle q is at position x equals 5 at time t equals 0. Question for part A. For 0 less than or equal to t less than or equal to 8, when is particle p moving to the left? So you want to be careful with this particular problem. You want to keep in mind the fact that we have two particles involved here. So some problems might involve just one particle, some problems might involve both. So pay close attention to the particle under consideration so you do not select the wrong function. Alrighty. In this particular part of question 5, we're dealing with particle p. So this position function is what we're going to be looking at. All right, when does the particle move to the left? Now, one thing you want to recall is the following. You want to remember that velocity is a vector quantity. It has both sign and the direction. Okay, sign and magnitude. Okay, it has magnitude and direction. Think about the direction as the sign. So the sign or the direction, the sign of the velocity basically tells you a very important information concerning the direction that the particle is moving. And that's what you want to remember. You want to remember that the sign of the velocity indicates the direction of the particle. All right, indicates the direction of the particle. In this case, we have a particle moving on a straight line along the x-axis. Okay, so it's either going to be moving to the right or moving to the left. So just to make a real quick connection right here, let's take a look at our fun chart real quick. So our fun chart, we have f concave up, concave down, f prime increasing, decreasing, f double prime positive, negative, f increasing, decreasing, f prime positive, negative. All right, so f1 chart can be adapted to CVA also, position, velocity, and acceleration. All right, so when you're going down, you're differentiating with respect to time. Now, the velocity, whether positive or negative, tells you if f is increasing or decreasing. Now, how do you adapt it to the position situation? If the velocity is positive, position increasing basically means it is moving to the right, okay, farther and farther away from the origin, okay? And when the velocity is negative, what does that tell you about the position? The position is decreasing, basically meaning that it is moving to the left, closer and closer to the origin. Basically, that distance from the origin is decreasing. All right. So when I say the sign of the velocity indicates the direction of the particle, if the velocity is positive, in this particular scenario, moving along the x-axis, positive velocity means you're moving to the right. Negative velocity means you are moving to the left. Okay. All right. So let's specify that real quick, what we just talked about. So if your velocity is less than 0 or negative, that basically means that you're moving to the left. And if the velocity is greater than 0, that basically means you're moving to the right. In this particular problem, we're looking for when the particle is moving to the left, basically when the velocity is negative. Alrighty. Okay, so let's go ahead and formulate our plan of attack, and then we're going to go ahead and solve this problem. So first things first, we want to figure out the points where the velocity changes sign and those are known as our critical values. So we want to find the critical values. The critical values of the position function, basically when its velocity is 0 or non-existent, okay? And then when we find the critical values, those are the boundary points, then we create intervals, and then we'll determine when the velocity, which is v sub p of t, is negative, okay? Because as indicated earlier, when you have a negative velocity, that is when the particle is moving to the left. Okay, let's do this. So we'll start off by finding the critical values. So part 1, find the critical values of the position function x sub p of t. The critical values are basically where, let's specify that, where the velocity or the derivative, okay, v sub p is also the derivative of the position function, where it's equal to 0 or where it does not exist, okay? Don't forget that. There are two parts in finding the critical values. All right, so let's go ahead and find it. First things first, we'll find the derivative, starting with the position function x sub p of t equals the natural logarithm of t squared minus 2t plus 10. So we're going to differentiate this using the chain rule. So remember, again, this was indicated earlier, but I'm just going to stress it again. If you have CVA, when you differentiate your position function with respect to time, that takes you to the velocity. Okay, and when you differentiate your velocity with respect to time, that takes you to your acceleration. All right, so don't forget. So when we're differentiating this, we are actually looking for the velocity. So the velocity of particle P, we've got to be specific here, which is equal to the derivative of the position function. Now this is a composite function, so we're going to differentiate using the chain rule. The outer function is ln, and the inner function is t squared minus 2t plus 10. So let's use the chain rule. We're going to do this real quick. The derivative of the outer is 1 over u, so it's 1 over the derivative of the outer evaluated at the inner. So plug the inner into the derivative of the outer, t squared minus 2t plus 10, times the derivative of the inner, which is just 2t minus 2. Okay, so let's write this nicely. This can be written as 2 times t minus 1 divided by t squared minus 2t plus 10. Okay, so we're still looking for the critical values. We want to find where the velocity is 0 or non-existent. So we have to split it up. We're going to look for where the position function, the derivative of the position function or the velocity is equal to 0. So for this particular one, we are going to extract the numerator. Okay, so basically look for where the numerator is equal to 0. So the numerator here is 2 times quantity t minus 1 equals 0. Let's solve that for t. Okay, divide both sides by 2. You have t minus 1 is equal to 0. Add 1 to both sides, you have t equals 1. Perfect. Now, this is one of our critical values. The next one, we're going to take the denominator. Basically, we're looking for when the derivative of the position function is not undefined, where it does not exist. Okay, so what makes a rational undefined? It's when the denominator is equal to 0. Okay, so in this particular case, we're going to extract the denominator, set it to 0, and see what we can do there. That will give us the critical values, additional critical values if they exist. Okay, you're not always guaranteed to have critical values all the time. All right. Okay, so here we take the denominator which is t squared minus 2t plus 10. That's a quadratic. Set equal to 0. Let's solve this. Let's try to factor. So make a nice little x game here. The AC method. AC is 10 and B is -2. So the factors of 10 are 110 and 25. None of them work. Okay, so this is prime. So it cannot be factored. So to solve this, we have to use the quadratic formula. Okay, so let's go ahead and use that. We're going to use the quadratic formula. Or you can use completing the square, same thing, okay? All right, so A is 1, B is -2, C is 10. Okay, so let's see. So x is equal to -b, which is +2. So x equals -b, which is +2, plus or minus the square root of b squared minus 4ac. C is 10 over 2a, which is just 2. Okay, if we simplify that, we have 2 plus or minus the square root of 4 times 10 is 40. 4 minus 40 is -36 over 2. Okay, all right, so let's simplify that. That's going to give us x is equal to 2 plus or minus. Okay, we have a situation here. We have imaginary roots. Okay, so whenever you have imaginary roots, they cannot be considered. We're only looking for real number values for our critical values. Okay, so this is 1 plus or minus 3i. Since it's imaginary or unreal or not real, that automatically tells us that there are no critical values that results in this expression being undefined in the real number line, okay, in the set of real numbers. So the only critical value we have is t equals 1 on that interval, okay? So let's specify it. The only critical value we have on that interval 1 to 8 is 1. Okay, so we want to go ahead and generate our interval, and we're going to be using the connection between the sign of the velocity to indicate the behavior of the position. Alrighty, so we have the behavior of the position function, and then we're going to have the sign of the velocity, which is equal to the derivative of the position function with respect to time. All right, so let's create our interval. So our interval goes from 0 to 8. So we're going from 0 to 8. We have only one critical value, which is 1. I'm just going to put it dead in the center. So this gives us two intervals. Okay, we have interval 1 and interval 2. So we want to figure out the sign of the velocity or derivative of the position on these two intervals, and that will tell us the behavior of the position either to the left or to the right. Okay, so let's pick our test values that we're going to be using. So between 0 and 1, I could use t equals 1/2, and between 1 and 8, let's pick something easy. Let's use t equals 2. So I'm going to be plugging these into the velocity function, which is 2 times t minus 1 over t squared minus 2t plus 10. Now remember, all I care about is the sign. Okay, so keep that in mind. All right, so if I plug in t equals 1/2 into this function right here, I'm going to have 2 in the numerator times, if I plug in 1/2, 1/2 minus 1 is going to be a negative result, okay, divided by, in the denominator, I'm going to have 1/2 squared, which is 1/4, minus 2 times 1/2, that's 1, plus 10. All I care about is the sign, okay? So I can see that the numerator is definitely going to be negative. Negative divided by, now in the denominator, what is the result going to be? If you have 1/4, 1/4 plus 9, because minus 1 plus 10 is 9, right? 1/4 plus 9 is positive 9 1/4. Okay, so positive divided by negative, negative divided by positive is negative. Okay, so in interval 1, the velocity or the derivative of the position is negative. Okay, so if you're using the fun chart, that will mean that the function is decreasing, right? But in the context of this problem, you know what it means? It means that the particle, oh wait, my arrows, funny, it's decreasing. In the context of this problem, rectilinear motion on an x-axis basically means that the particle is moving to the left. Okay, so negative velocity means you're going to the left if you're moving on a straight line. Your distance is decreasing, okay? All right, okay, let's look at interval 2. If we plug in 2 into the function, remember all we care about is the sign, okay? So we have 2 times 2 minus 1 is positive 1. And then in the denominator, we have 2 square. Let's just work that out mentally. So 2 square is 4. 4 times 2 times 2 is 4. 4 minus 4 plus 10. So the numerator is positive, and the denominator is 0 plus 10, which is also positive, which is positive. So that tells us that the function is increasing if we're using the fun chart, but in the context of this problem, it basically means that the particle is moving where? To the right. Okay? So the question asks, when is the particle moving to the left? So basically looking at where the derivative is negative, and that is on interval 0 to 1. Okay? So let's write down our answer. In justification, the particle is moving to the left on the interval 0 to 1. Why? Because the derivative is positive there. Okay, because it's negative. Because x prime of p is less than 0 there. Now in this particular problem, you are not asked to provide justification, but it's just good practice just to put the justification there. You know, a good habit, just in case a question asks for justification and you forget, but if you have the habit of doing that, you can just include that in the answer and you get it correct. All right, so how was this problem scored on the 2017 AP exam? Well, this is how it was scored. This was a 2-point problem, okay? You got 1 point for finding the derivative, the velocity function correctly, so that was a 1 point. And then by looking at the intervals where it's negative, you get another point. So all this entire work here gets you another point for a total of 2 points for question 5A. All right, let's take a look at 5B. The question reads, for 0 less than or equal to t less than or equal to 8, find all times t during which the two particles travel in the same direction. Okay, so let's go ahead and outline our plan of attack here. So one thing we want to do first is we want to isolate the velocity function of the two particles, okay? So find the velocity function of the two particles. Now the question is, why do you need that? Well, as indicated in part A, the sign of the velocity tells us the direction, okay? So after finding the velocity function of the two particles, we're going to determine the intervals where what? Determine the intervals where both functions have the same sign. All right, where both functions have the same sign. Okay, So let's do it. We already have the velocity function for particle P. Not only that, we also know the signs. We know the direction in part A. We already did that, okay? So if we look back, we know that it's going to the left on interval 1 from 0 to 1, and it's going to the right from 1 to 8. So we already have that, which is great. So that saves us time. So let's write that down, what we already know. We already know the sign chart for the velocity of particle P, which is x prime of particle P. We know that, let's just make a real quick sketch here. We know that from 0 to 1, it has a negative sign, which means it's going to the left. And then from 1 to 8, the velocity has a positive sign, which means it's going to the right. So our focus now, or most of the work, is going to be with particle Q. Okay, so for particle Q, what do we have? For particle Q, we are already given the velocity function, so no need for differentiating here. We're given the velocity function as t squared minus 8t plus 15. So all we just have to do is find the critical points and create a sign chart. All right, so let's find the critical points. Okay, so basically we're looking for where the derivative v of q is equal to 0 or where the derivative v sub q does not exist. Okay, so we're looking for the critical points of the position function of particle q. Okay, so if you differentiate the position function of particle q, then you have the velocity functions which we were given. Okay, so we have t squared minus 8t plus 15 equals 0. So there's the velocity function. Just imagine as though it's over 1, okay? So just take the top for when it's equal to 0, and let's play the x game. All right, let's play the x game here. So what do we have? AC goes on top. AC is 15, and B goes on the bottom, negative 8. 3 times 5 works here. Fix the sign, they're both negatives to get negative 8. There you go. Okay, so since A is equal to 1, we don't have to group. We just go right to the factored state, which is t minus 3 times t minus 5 equals 0. Solve that using the zero product property. You have t equals 3 and t equals 5 as the critical values for where v of q is equal to 0. Now, where v sub q of t does not exist, for that one, we're looking at the denominator when is equal to the denominator. So the denominator is 1, and when is 1 equal to 0? Never. So there are no values where this where the position function is undefined. Okay, this is a polynomial function, and we know that polynomials are smooth and continuous. They don't have any funny things happening with them. Okay, as defined on the entire domain. So we have our critical values. Now we're going to set up our chart to determine the signs. Okay, so I'm just going to do them separately. You can do them together if you want, but I want to do it separately so I don't get my work confused. Let's deal with the signs for particle Q first, and then we'll combine that with particle P and then see where they match up. Okay, all right, so for particle Q, we have, let's see, 0, 3, 8. So we have 0, go from 0. It goes from 0 to 8, right? And then we'll break it up. We have 3, and then we have 5. So basically we have 3 intervals to look at. Okay, interval 1, interval 2, and interval 3. All right, so we're looking at the sign of sine of v sub q. Okay, we're going to be using the factored state because it's much easier to deal with it, to figure out the sign there. So t minus 3 times t minus 5. That's what we're going to be plugging in. So for the first interval, we're going to use t equals 1. So remember, all we care about is the sign, okay? So when we plug that in here, 1 minus 3 times 1 minus 5, we can easily see that we're multiplying two negatives. Negative times negative is positive. So in this interval, the particle is moving to the right. Interval 2, plug in what we're going to use here. How about we just use 4? Plug 4 into your velocity function. You have 4 minus 3 times 4 minus 5. So you subtract this. This is going to be positive times negative, which is negative. So the particle is moving to the left on interval 2 for the particle q. And then for interval 3, let's use t equals 6. Plug that in. We have 6 minus 3 times 6 minus 5. Okay, so this is positive times positive, which is positive. The particle is moving to the right on this interval. Okay, all right, so now what we're going to do is we're going to find the union of the two number lines and see where the signs are the same, and then that will help us to know when they are going in the same direction. All right, so I'm going to put the one for particle Q on the top. I'm going to put particle P on the top and then Q on the bottom. Okay, so this is for V of P. So for V of P, going from 0, we had a critical value at 1. Okay, we did that in the previous problem, to 8. So remember what we did. It was negative here on this interval, and then on the other interval it was all positive. So positive, positive. That's for V of P. Okay, and then let's look at V of Q. So for V of Q, that's what we just did. We have two critical values for this one. We have this one 0, we have 3, and we have 5, and we have 8. Okay, so based on what we have up here, from 0 to 3 it was negative. 0 to 3 was negative. All right, so negative, let's see where my thing go. So negative, negative, and then 3 to 5, oh, I'm sorry, it was positive. Let's do that again. So for 0 to 3 was positive, and then from 3 to 5 it was negative, and then from 5 to 8 it was positive. All right, so let's unite them together. Okay, and then we're gonna see what where they have the same signs. Make my lines pretty skinny here. Okay, so we go just extend one to this one right here, and then extend that one. Let's do it again. Extend that one down here, and extend that one down here. Okay, so let's look at the different signs, see where the signs match up. That's basically what we're looking at. So here we have minus, and then here we have minus, and then here on the top, here we have plus, 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 and then here down here we have plus here, we have plus here, and then we have plus here. So where do we have a match? Identical signs. That's what we're looking for. We can clearly see that we have identical signs here where both particles are going to the right, and identical signs here again where both particles are going to the right. So those are the intervals where the particles are moving in the same direction. Okay, so let's go ahead and write down our answer. The particles are moving in the same direction on the intervals 1 to 3 and oh snap, 3 is not included. 1 to 3 and 5 to 8. Why? Just put the justification there, because their velocities did what? Their velocities have the same sign. Have the same signs on those intervals. That's why they're moving in the same direction. Remember, the velocity, the sign of the velocity tells you the direction that a particle is moving. All right, on the AP exam, this problem was worth 2 points. Okay, so you get 1 point for finding the intervals, which is this right here, and then you get another point for analyzing the intervals, basically using the signs from the intervals to arrive at your conclusion, for a total of 2 points. All right, let's take a look at part C. Part C says find the acceleration of particle Q at time t equals 2, and is the speed of the particle Q increasing, decreasing, or neither at time t equals 2. Okay, so let's go ahead and outline our plan of attack here. So first of all, we're going to have to find the acceleration function. Okay, for Q, find acceleration function, and then next we're going to evaluate the acceleration at the specified time t equals 2, and then 3, is it increasing or decreasing? Well, in order to do that, we're going to compare the signs of the acceleration and velocity at time t equals 2. All right. To answer the final question, we're going to compare the signs of acceleration at 2 and velocity at 2. And that'll give us the answer. All right. Okay, so let's get started. What were we given here? We were, for particle Q, we're given the velocity function, v sub q of t is equal to t squared minus 8t plus 15. And how do you find the acceleration from the velocity? So we're going to use CEVA again. So we have CEVA. We know that if you're at your velocity and you want to find acceleration, you're going to differentiate with respect to time. Okay? All right, so let's go ahead and do that. We're going to differentiate our velocity function with respect to time. Okay, so we have, let's see, what do we have here? We have the velocity function, v sub q of t. Now we're going to just apply the power rule here to find the acceleration. So a sub q, acceleration of particle q, with respect to time, is v prime of particle q with respect to time, which is 2t minus 8. Alrighty? So the acceleration of particle Q at time 2, which is step 2, evaluate. We're just going to plug in 2 for t, and then use our order of operations to finish this off. Okay? So 2 times 2 is 4. 4 minus 8 is negative 4. So there goes the acceleration. That's the first answer. And then next, we need to find if the particle is increasing or decreasing, or neither. All right, so to answer that, you need to recall that the speed increases when acceleration and velocity have the same sign. Okay, have the same sign, and vice versa. And decreases when different. All right, so from the previous example, we know that v sub t for particle q, the velocity at 2, what was it? Let's look at it real quick. So for particle q, the velocity at 2 is right here. Oh wait, it's right here. It's positive. Okay, so it's positive for that. And then what's the deal with the acceleration? So velocity at 2 is greater than 0. And then the acceleration, what's the acceleration of particle Q at 2? The answer right here, -4, is less than 0. Signs are different. So what does that mean? That means that the speed is decreasing, or the particle is slowing down. Okay, so let's write that down. Since the velocity and acceleration have different signs, the speed of particle Q is decreasing. Or another way that is normally phrased in the AP exam is that the particle is doing what? Slowing down. Slowing down. Okay, so that's that for this part. Okay, so this one is a 2-point problem. To get your first point, you have to find the acceleration and evaluate it at 2, and you get 1 point here. And then secondly, the second point is by comparing these two and explaining the reason why the particle is experiencing a decrease in speed. So there you get another point there for a total of 2 points. All right, let's take a look at the last question. So in this question, we are asked to find the position of particle Q the first time it changes direction. Okay, so let's outline our plan of attack here. How we're gonna solve this problem. Let's see. So first things first, we need to figure out when does a particle change direction? When is the first time? Okay, so plan is 1, find the first time. Find the first time the particle changes direction. Okay. And then we're going to find the position of the particle at that time. Okay, so determine the position of the particle at that time. Position of the particle at that time. Okay, so when does the particle first change direction? The particle Q first changes direction when the velocity first changes sign. Okay, and now we can consult what we did in problem part B to determine the answer to that. So let's go back to part B. So in part B, for the velocity function of Q, we know that at time t equals 3, the sign of the velocity changed from positive to negative, and then at t equals 5, it changed from negative to positive. So the first time is at time t equals 3. So that's what we are going to use for this problem. Okay? All right, so from part B, we know that, what do we know? We know that the particle first changes direction where? First changes direction at time t equals 3. All right, so we now know the target time right now. Okay, so that's that with part 1. Okay, so for part 2, we now need to find the position of the particle at that time. Okay, so if you're given a velocity and you want to find the position, how do you do that? So let's use CEVA again. So you're given velocity and you're going to position. In order to do this, you are going to do the inverse of differentiation, which is integrate. You're going to integrate your velocity function, and don't forget to add your initial position. Okay? So that's how you do it. So for CEVA, when you're going down, you differentiate, yeah? And then when you are going up, you integrate. That's basically how it works. Okay, so we're given velocity function here, and then we're just going to find the position at this particular time for that. Okay, so let's go ahead and write down the formula. It's going to involve an integral for finding the position of a particle at a time A, let's say at B, okay, is equal to the position at B. Position at B is equal to the integral from A to B of V of t dt. So the displacement plus the initial position, which is x of A, like that. Okay, so that's how we're going to do it. Now, in this particular problem, we have the velocity function. Let's rewrite the velocity function again. So v sub q is t squared minus 8t plus 15. So we have the velocity function. We need a. A is the lower bound on the interval. So we know what the position was at 0, right? So we're just going to use that. So we're going from 0, a equals 0. B is 3. And then the position at A, x of A, is x of 0, which is 5. We know this. This was given to us, so that's why we're using it, okay? And then guess what? X of position at B, which is x of 3, is what we're looking for. So x of B, which is a position at 3, is a question mark. Okay, so let's set it up. X of 3, using the formula above, is equal to the integral from the lower bound 0 to 3 of the velocity function t squared minus 8t plus 15 dt. And please do not forget to add this piece, x of 0, which is 5, your initial position. Very important. All right. Okay, so let's go ahead and integrate this. We're going to be using FTC 2 right now. I'm sorry, FTC 1. So when you integrate this quantity with respect to time, you have t to the third over 3 using the power rule minus 8t squared over 2 plus 15t. And this is evaluated from 0 to 3. And of course, we do not want to forget our nice little plus 5 here. Okay? All right, so we're going to just plug in the top and then the bottom and then find the difference, okay? So the antiderivative of the upper limit minus the antiderivative of evaluated at the lower limit. If we plug in the upper limit, we have 3 to the third over 3 minus, so these two divide out, can reduce that to 4, minus 4 times 3 square plus 15 times 3. Now, if you plug in 0, all of them have t's in them, right? So what does that mean? It's all going to be 0. So minus 0 plus 5. Okay, so we're going to use PEMDAS, order of operations, to simplify this. So we have 3 squared over 3 is 9, minus 3 squared is 9 times 4, 36, plus 45, plus 5. And if you do the arithmetic, you will end up with, let's see, 23. Bam. Okay, so there is the final answer to question number 5D. Okay, so this particular problem was a 3-pointer. Okay, you get your first point by finding the antiderivative, which is this piece right here. So you get 1 point. You get another point by using the initial condition, x sub 0 is 5. This piece I told you not to forget. And then you get another point by getting the correct final answer, which is 23. So for a total of 3 points. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming calculus exam, do give us a like or thumbs up. Your positive feedback is very valuable to us. Don't forget to post any comments about this presentation or any questions you have about calculus in general, and we'll be more than glad to respond. Don't forget to subscribe to our channel for updates to future uploads. We upload videos to our page on a weekly basis. More valuable resources can be found at mathgotserved.com, or just take a look at the link in the description below. Thanks again for watching and have a wonderful day. Goodbye.